Let's consider propene-propane separations. Most of the available adsorbents are selective to propene, and therefore the desired propene product can only be recovered in the final vacuum blowdown stage. Here is a typical PSA scheme for propene-propane separations described in the paper by Khaligi. The 5 stages consist of pressurization, followed by an adsorption cycle in which propane is removed from the top of the column. The adsorption cycle is followed by a co-current high pressure purge with propene in order to remove any adsorbed propane in the pores. This is followed by a co-current blowdown step, and finally a countercurrent vacuum blowdown is used to recover propane of the desired purity. The product purity is dictated strongly by the amount of propane that is still present in the void volume and in the pores in this final countercurrent vacuum blowdown step. Therefore, it is important to have an adsorbent material that completely rejects propane into the gas phase and is highly selective to propene. One such material is chabazite, and that is the material also described in detail in this paper. Here's the structure of chabazite. Consists one unit cell of chabazite has 6 cages. Each cage is separated from an adjacent cage by narrow 8-ring windows. But the cage volume for chabazite is slightly larger than for DDR zeolite, but significantly smaller than for fluxes. Chabazite zeolite, suggested as an adsorbent for propene-propane separations, with a cage-type zeolite where adjacent cages are separated by windows which are 4.2 angstrom in this direction and 3.8 angstrom in this direction. Due to subtle differences in the bond angles and bond lengths between propene and propane, the ratio of diffusivity of propene to propane is a few orders of magnitude high, as reported in this paper by Ruthven and Reyes. And therefore, due to the high ratio of diffusivities, it is possible to construct a kinetic separation scheme for propene-propane separations. Let's look at transient uptake of a mixture of propene and propane in all silica zeolite. The simulations of the transient uptake were carried out using the unary isotherm data along with the diffusivity data from the paper by Khaligi. Let's have a look at the animation for the transient uptake. This is the surface of the particle. The red line shows the uptake of propene that has a diffusivity 5,000 times larger than the diffusivity of propane. Propene penetrates into the crystal and achieves supra-equilibrium loadings significantly higher than the loadings at equilibrium corresponding to the loading at the surface. Note also that for a 50-50 mixture in the gas phase, the loading of propane at the surface is larger than the loading of propene. And when equilibrium is reached, the crystallite of chabazite is richer in propane than propene. The spatially averaged component loadings are plotted here. In black are the simulations that include thermodynamic coupling effects, and the lines colored blue are simulations in which thermodynamic coupling effects are ignored, and the simulations are based on the assumption that the matrix of thermodynamic correction factors is the identity matrix. Taking proper account of thermodynamic coupling effects leads to significant transient overshoots in propene and the attainment of supra-equilibrium loadings that are about a factor 3 to 4 times larger than the value at equilibrium. In the previous slide, I had demonstrated the importance of taking proper account of thermodynamic coupling effects in modeling transient uptakes within single crystals of chabazite zeolite. In previous publication, I had also examined the importance of thermodynamic coupling effects on kinetic separations in PSA technology. It also considered the need for including thermodynamic coupling effects in modeling the PSA technology for separating propene-propane mixtures using chabazite zeolite. This material is also available in a previous video presentation, C3H6, C3H8 separations with chabazite zeolite, on my YouTube channel. Today, I'm going to demonstrate the importance of thermodynamic coupling by performing pulse chromatographic separations in a fixed bed packed with chabazite zeolite. The feed mixture is a 50-50 mixture of propene and propane at a total pressure of 200 kilopascals and at a temperature of 353 Kelvin. Rather than using a step input of the feed mixture, as was done in the material listed here, this is my paper and also my earlier video presentation, today I consider a pulse feed wherein the duration of the pulse is 1000 seconds. I perform 3 types of simulations, as I will describe in my next slide. The pulse chromatographic simulation results for 3 different types of model implementations are shown here in the 3 graphs. Graph A is the result obtained by a model in which thermodynamic coupling effects are properly taken into account, and the intra-crystalline diffusivities of components 1, which is propene, component 2 as propane, are the same as those used in the transient uptake simulations presented a couple of slides ago. The feed mixture is a 50-50 mixture at a pressure of 200 kilopascals and a temperature of 353 Kelvin. And the pulse lasts for 1,000 seconds, and then the contents of the bed are evacuated by application of deep vacuum. Let's examine the results for the scenario in which the Maxwell-Stefan formulation includes thermodynamic coupling effects as calculated using the mixture adsorption equilibrium data described in my published papers. The breakthroughs from the pulse chromatographic simulations show clear separation of propane, indicated in blue, and propene, indicated in red. The pulses are distinctly separated from one another, and this demonstrates the phenomena of kinetic separations in which the more poorly diffusing component, propane, that has a diffusivity 5,000 times lower than that of propene, is rejected into the gas phase much earlier, and the more mobile propene remains in the pores or transfers into the pores much quicker and elutes the column much later. If thermodynamic coupling effects are ignored, we get the breakthrough curves shown here, where the elution of propene, indicated in red, occurs during the same time interval during which propane is eluted. In other words, the separation is certainly not sharp. The third scenario is a model in which intra-crystalline diffusion limitations are ignored, and the ratio of the Maxwell-Stefan diffusivity for each of the components divided by the square of the crystallite radius has a very large value. This implies that the surface of the crystallite is in equilibrium with the gas phase mixture, and that there are no diffusional limitations inside the particle. In other words, there are no concentration gradients or loading gradients within the chabazite crystallites loaded into the fixed bed. The separations are purely based on thermodynamic equilibrium that favors propane, and therefore the component to elute first, the first peak, is due to propene, and propane elutes much later. So for kinetic separations, it is important to take thermodynamic coupling effects into account to obtain clear separation between the two gas molecules. This is the same conclusion that emerges from simulations of PSA. But let's look at the animations of these three chromatographic separations to get further insights into the movement of the pulses along the length of the fixed bed. Let's first examine the results for the pulse chromatographic simulations in which thermodynamic coupling effects are duly accounted for. The blue lines represent the concentrations of propane in the gas phase, and we see that propane exits the column much earlier than propene, because propene is more mobile and enters the pores very quickly, whereas propane is virtually excluded from the pores. This time the feed mixture is stopped, and the pulses elude the column, and the first pulse to elude the column is the blue one, which is due to propane. Let's have another look where I at this time the feed pulse is stopped, and we see that the blue exits the column first, and when propane exits the column, only then does propene leave the column. So the separation between the two peaks of propene and propane, rather propane and propane leaves first, propene is the second one to leave, occurs at distinct intervals. Not so if thermodynamic coupling effects are ignored. And let's have a look at the simulations where we use the Fick's law and ignore thermodynamic coupling effects. And if we examine the simulation data, we see that when the feed mixture pulse is stopped, the two components, propane indicated in blue and propene indicated in red, exit or eluted almost together, and these peaks are overlapping, and the separation is therefore much less effective. Rather, it is ineffective. Therefore, kinetic separations require proper account being taken of thermodynamic coupling effects. Let's look at the third scenario, in which intra-crystalline diffusion effects are completely ignored. In this case, the component to elute first is the red one, which is propene. And only when propene is eluted does propane exit the column. So we see that the separations that are based on differences in diffusivities require us to take proper account of thermodynamic coupling effects for good separations to be achieved.